We introduced the basics of wireless LANs in the last lecture last week, where we spoke about the characteristics of data rate, transmission range, transmit power. It's a summary of some of the characteristics, and we spoke about what we're going to assume about the physical layer. We have a physical layer that is specific, or there are different physical layers available, 11A, 11B, 11G, use different technologies to provide different data rates and transmission ranges. We saw a comparison of them. The medium access control layer controls who can transmit at what time, and also controls how stations or clients join a wireless network. And that's what we'll go through briefly now, and then we'll go into the data transfer. That is, we'll focus first on the management procedures. How do I discover a network, join a network, and leave a network? And we finished last week with an example where we captured some wireless LAN traffic in the SIT network and saw some of the frames which were transmitted. Let's now talk about the procedure, how it works. Where we're focusing on the management procedures for now. Discovering, joining and leaving a basic server set or an extended server set. The basic server set is provided by one access point. The extended server set is when you combine, for example, all the access points in SIT are under the one name, WSIIT. That's the extended server set. There's two ways for your client to discover an access point. A periodic broadcast of beacon frames by the access point, telling whoever receives that beacon frame that it's an access point and potentially available to connect with. And the other one is proactive by the client, where the client broadcasts a probe request. When I say broadcast, when we talk about wireless LANs, we often think that every transmission is broadcast. That is, when I transmit from the physical layer, potentially anyone within range can receive that. When I say broadcast here, I mean that the destination address is a special address that means anyone can process that frame even if they receive it. The address is, if you recall back to IP addresses, we had some special cases. There was a 255, 255, 255, 255 address, which is a broadcast address. The same for MAC layer transmissions. There's a special address for broadcast. It's the all ones address. A MAC address has 48 bits. The special address where we have 48 ones means broadcast. In hexadecimal, that's all Fs. And one more. F as a hexadecimal digit is 15. In binary, 4 ones. And if we keep going, it turns out to be 48 ones. That's the special broadcast address for the IEEE 48-bit addresses, both for an Ethernet wired LAN and for what we're focusing on today, a wireless LAN. What that means, if my client laptop creates a frame and sets the destination to this special broadcast address, I transmit that. Anyone within range will hear that. Your laptop, your mobile phone, the access point out that corridor, the access point upstairs, if it's in range, will receive that frame and they'll process that frame. Because it's the broadcast address, it means when they receive it, they will process it at the MAC layer. A non-broadcast address, as a random example, if I transmit a frame with this as the destination address, a non-broadcast address, I transmit it from the physical layer's perspective, your laptop receives it, your mobile phone receives it, and the two access points receive it. But because only one of them may match this address, the other three will discard that frame. They will not process it. So there's a difference between physically receiving the frame and then processing it. If it's destined to you, you can process it. So if this is the destination address and your device has this address, then you will process that frame. Or if the destination address is a broadcast address and you receive the frame, then you'll process it. So that's a way to send to multiple destinations at once. And that's what's used with both the beacons. A beacon frame sent by an access point is sent to the destination broadcast address, the all ones address. Any client that receives it will process it and know that there's an access point nearby. Similar, a probe request frame sent by my client is sent to the all broadcast or all one broadcast address. Anyone who receives it will process that. Now, your mobile phone or laptop may receive and process it, but they may not do anything with it. They don't care that my laptop is looking for an access point. Your mobile phone may look at it and they may discard it. An access point that receives the probe request will look at it and realise that there's a client searching for an access point and may respond with a probe response frame. And I will receive the probe response, and when I receive that, I've discovered the access point. Two ways to discover access points. Once we discover the access point, we associate with it. We create a connection with that access point before we transfer data. And there are two steps there. Authentication, so the access point can check whether we're allowed to join the network, and association, that is just registering the client with the access point. Once we've done those steps, then we can transfer data. We transfer our data maybe for one second, for 1 minute, for 1 hour, and eventually maybe you shut down your laptop, you want to go home, then there's a process of de-authenticating and disassociating with the access point, to telling it that I'm no longer going to connect with you, and therefore you remove the information about my association and authentication. And in fact, either the client or the access point can initiate that. Let's have a look at the exchange, which illustrates those frames being sent. This illustrates a periodic broadcast of the beacons by the access point. That is, it doesn't show it very well, but the access point is, if it's configured in that way, is always sending a beacon frame. A default value may be 10 per second. So every 100 milliseconds, an access point sends this special frame, and whoever receives it discovers that access point. This doesn't show the probe request or probe response. We can use one or the other or both. It depends upon the configuration of the access point and the client. Once I discover an access point, my client then joins with that access point. It sends an authentication request frame to the access point, possibly providing some authentication details, some credentials, to prove who I am. Access point can check that information and send back a response, successful or not. Are you authenticated or not? And if successful, then I will send an association request frame, and if everything's okay, not from an authentication perspective, but maybe from a resources perspective, maybe the access point only supports 10 clients to connect at once. When it receives the association request, maybe it already has 10 clients connected already. It may send back a response saying, no, you cannot associate. But if everything's normal, then we'll receive an association response, and we're now associated with that access point. And we can transfer data. So we transfer data, and at the end, when we want to no longer transfer data, we may disassociate or deauthenticate from either side. The access point may kick me off the network by deauthenticating my client, or I may leave the network using either of the messages. Most likely an access point will have a timeout as well. If you don't send anything for maybe 5 minutes, it will automatically deauthenticate you or disassociate you. It's up to the implementation of the access point, how to deal with that. So these are some of the management frames available or used in a wireless LAN. Let's look at an example of our capture, if I've still got it from last week, or an old capture that shows some details of some of those frames. Do I have from last week? When was our lecture last week? Can anyone remember what day? 19th? 19th. Let's try file 1. That's file 1 is the capture from last week. Let's see if we have anything interesting in there to see. I'll open that capture. Note that what Wireshark does. Who has taken my lab? Were you all in the lab? Some of you were. Okay, some have it on Friday, tomorrow. But what Wireshark does is tries to convert some of the addresses like this into addresses which are more human readable. I'm going to turn off those features just for now, this name resolution. Have I got the right one? File 1. This is the set of frames or packets that were transmitted while we captured last week. That is, I was using my laptop wireless LAN to record all the packets that were transmitted in the nearby wireless devices. I've got 2 wireless devices. This one is my second one. And also when other people were transmitting and I was within range, I could capture their packets as well. Where do we go? There are many different packets captured. There were thousands, 76,000 packets captured during that several minutes that we captured from many people transmitting. Let's see if we can find some regarding to wireless LAN transmissions. If I can remember the commands. What are we looking for? I want to filter out and select only some packets which are useful for demonstrating for this wireless LAN setup. And the filter is, and then that's the wrong filter, but I'll show you the right one. I want to show the wireless LAN frames. FC refers to frame control, which is a field in the header of a particular type. There's 3 types. Type 0, which are the data frames. Type 1 are control frames like acknowledgements. We've got many acknowledgements here. And type 2 is what I want, is beacons, management frames. show only the packets captured which are wireless LAN management frames. Management is setting up the network, joining, leaving, discovering. Let's hope we have some. Do we have some? Why are they? I've done it wrong again. Frame type 2. Sorry, there are 3 types. And let's write this on the board. Type 0, type 1 and type 2. 0 management. 1 control. And 2 is data. That is, data is once we transfer data, they are considered type 2. Type 0 is things like beacons, probe requests and responses, so probes, and there are others as well. Control, acts, acknowledgements, and a few others as well. Here I've selected type 0. If you haven't seen Wireshark, then you'll see it in the lab on Friday. It lists the set of frames that my wireless device inside the laptop captured during some period of time, several minutes while we ran the test. We see here's the source address of someone who transmitted a frame and the destination address. And we see it's a beacon frame. And we see that the destination address is our all ones broadcast address. So this was sent by an access point identified by this address to everyone within range. It happened to be my laptop was in range at that point in time. It's a beacon, and we'll see that there are more from different access points and also from the same access point. The second frame number 47 here is from an access point different from frame 18. You can notice by the different address, the last 4 digits on the address, the last 2, B04C. But here, frame number 159 is the same source as frame number 18. That is, over these 5 or 6 frames, there are 2 access points sending beacons. This was performed upstairs on the 5th floor, so at that point in time I captured from 2 different access points sending beacons. How often are they sending beacons? What do you think? What do you think that those access points are configured to in terms of how regular they should send a beacon? Not 10 milliseconds. Note that there's 2 access points there. Just look at the first 5 frames, but maybe pick the frames belonging to just one source. B0, B0, B0. First one sent by B0 is at 0.024. The second one by B0, frame number 159 at 0.124. And the third one by 0.229, approximately every 100 milliseconds. 0.024 plus 100, 0.124 plus 100, 0.224. It's 0.229, so it's not exact. We'll see later that if someone else is transmitting, then it may delay the access point from sending the frame. But it's approximately every 100 milliseconds. When you configure your access points for your assignment, you'll see that configuration setting, and that's the default on most devices. 10 per second. And we also see some other management frames from 291, 292, 293. Someone sent some probe requests. These are probe responses sent by an access point. So I did not capture, in this case, the probe request, but I did capture the probe response. Maybe our network looks looks like this. If here's my laptop and I was capturing anything within range sent by any access point or client, from the first 5 frames it looks like there's an access point transmitting. Let's name it B0. The last 2 digits of the MAC address are B0. And somewhere else there's another access point transmitting 4C. So I've received those transmissions. That is, within range of those 2 devices. And then we see frame number 291, and the ones after that were sent also by 4C to 40A6, some other address. Whose address was that? I don't know. I don't think it was my address. My address is... I can check the address of my... The address of my 2 wireless LAN cards are shown here. WLAN 0 and WLAN 1. The WLAN 0 is on board or inside my laptop. WLAN 1 is this external USB wireless LAN device. 0026, 95 and 69. They are the MAC addresses of my 2 devices. Here is a frame sent by an access point, 4C, to this other address. And it's a probe response. So it's sent to some client. Some client, identified by 10 at the end, sent a probe request, and an access point received that probe request and responded with a probe response. Where's the client? Where's this one, 10? Where? Yeah, so it could be one of you or someone in another room. Where do you think it is relative to my laptop on this network diagram? The physical location relative to the other devices. Not for sure, but most likely it's outside of range of my laptop. Maybe somewhere over here. Why? Because I didn't receive the probe request. That is, I see that here is a probe response sent by an access point to someone named 10, or their last 2 digits of their MAC address is 10. I can capture that. And remember, with wireless transmissions, every transmission is broadcast. So when this access point transmits, it transmits to here, but the signal, it goes everywhere around it, including going to my laptop. So the probe response, although the destination address is this 10 device, some laptop somewhere else, because the wireless signal is broadcast, that is transmitted all around, then my laptop captured that and took a copy. So I received the response, but I did not receive the request. Because if there's a response, there should have been a request, whereas a probe response comes as an acknowledgement to the request. So most likely there was a request, a probe request, sent by a laptop to all the access points around. This one received it, others may have as well. This one responded. I drew the laptop 10 here because since I didn't receive the probe request but received the probe response, that suggests that my laptop is within range of the access point but outside of the transmission range of the laptop 10. That is, this one transmits, this one is within range, it receives the signal. If the signal keeps going, it's too weak for mine to receive. Let's say our range, to make things simple was 10 metres. So if these are within 10 metres, and I'm within 10 metres of this, I'm within 20 metres of, or it's 20 metres to the other client, outside of range. We'll see that this scenario, two clients within range of an access point but outside of range of each other, causes some problems with performance sometimes. It's called the hidden terminal problem. But we'll cover that later. We see some probe responses, and if we scroll down, I'm sure we may see other possibly requests and responses. Yep.
Why did the AP send so many probe responses to only one device?
It may be the configuration to make sure it receives it. That is, it's treated like a beacon frame. It's advertising itself. So send multiple probe responses, make sure it receives that. There may have been multiple probe requests. I don't know. We don't know from this capture. If this one sent multiple probe requests, then maybe it responds for each of them. I don't think it's specified how to do it. It's up to the implementation of the device as to how many responses to send. It may be that the client never attempted to associate after receiving the response. We don't know for sure in this case. We see they're quite close to each other, within several milliseconds of each other. Let's expand one of these beacons. So we've selected the top beacon, and here we can expand and look at the structure of that frame, the header fields. It's a frame with some fields that contain the different information, and that information is shown in the fields here, or the lines here in the middle of the screen. The frame is 106 bytes in length, so that's the size of this beacon frame. Some of the things it contains, I'll just expand. Frame control. There's a frame control field, a sequence of bits that indicate what type of frame it is. The version of the protocol being used, version 0. The type, that's this value, type 0. So anything that is a management frame is type 0. A beacon is a management frame for managing the network. Subtype tells us it's a management frame and the subtype is 8, meaning it's a beacon. The probe request and response have a different subtype. So these numbers of type and subtype simply indicate what specific type of frame it is. And that's why I did this filter up here. Wireless LAN, frame control, type equals 0. Show me only the frames which are management frames. That was the objective of that filter. Flags. On the slides we'll see the structure of these, but let's go through this example. Inside the frame are some flags, that is some 1-bit values, or in some cases a multi 2-bit value, that indicate whether this frame has certain features or not, or the access point sending this frame has certain features. Some of them, or they are listed here. We'll see whether the direction of this frame, and this is particularly useful when sending data, is it going to the client or coming from a client? We'll come back to that. Sometimes we use fragmentation. We have some data, the frame has a maximum size. If the data is larger than the maximum size, we need to fragment that data. If this bit is set to 1, it means that there's some fragmentation being performed. If it's a retransmission, we have power management features built into wireless LAN. My client, sometimes we'd want to save power and we turn off the radio every so often and only wake up to receive frames. If I turn off the radio, I save power and save battery, so my battery will last longer. Same with a mobile phone. So wireless LAN has inbuilt power management features such that a device can sleep, that is turn off its radio or put it into sleep mode for some period of time and then wake up to receive frames and then go back to sleep. This frame, or this bit, indicates whether power management is being used or not. Not in this case, it's 0. And some other fields which we'll see when we look at data. This is just a beacon frame. Duration, not relevant for the beacon. It's relevant in data frames. Destination address, the broadcast address, the source, the address of the device that sent the frame, in this case the access point, and the BSS ID, the identity of the basic server set, and it's also the access point MAC address. The basic server set is every access point creates a basic server set, and the identity of that basic server set is the identity of the access point. So these two values are the same. If we had fragmentation, we'd have a fragment number and a sequence number. And we see up the top, sequence number 2813, 2450, so it increments a sequence number. And there are some other parameters included. Some timestamp to indicate the time from the perspective of the access point. The beacon interval, how often it's sending beacons, every 100 milliseconds. Yeah. It's a binary value. Something about the capabilities of this access point, what features it supports. Some of them, let's see what we can talk about. So some of them are extra features supported by access points and wireless LANs. Anything that we've seen before. Something to indicate that this is an access point. An IBSS is an independent basic server set. That's what's sometimes referred to as ad hoc mode. When we connect my laptop directly to another laptop via a wireless LAN link, we say they're in ad hoc mode, not to an access point. So that's another way to configure wireless LANs direct between clients. And some other features of the access point. Does it support, or is encryption turned on, and so on? If these are set to 1, then that feature is turned on. Does it allow for dynamic changing of the channels, management of the channels, and different features? Anything else that we can find down the bottom? The final set of parameters. Here we see the name of the extended server set, WSIT. So this is an access point within the WSIT extended server set. And that's why your device knows when it shows on the screen which network you can choose the network, because the access point has told you that it belongs to this extended server set. The different physical layer, technologies support a maximum data rate that we've mentioned, like 11 megabits per second, 54 megabits per second, and so on. But that's the maximum. They in fact support a range of data rates. And this lists the range of data rates that are supported by this access point, from 1 up to 54 megabits per second. The basic concept is that the better the signal, the higher the data rate we can achieve. Or the closer you are to the access point, the higher the data rate. So if I had my laptop here and my access point here, I'm very close, strong signal, I can get the maximum data rate, say 54 megabits per second. If the access point is out in the corridor, maybe the signal is too weak to receive at that high data rate of 54 megabits per second, so we can automatically drop down to a lower data rate, say 36, 18 and so on. So we've got this, what's called ARF. What's ARF stand for? Anyone? Automatic rate fallback. Automatically fall back to a lower data rate. So the devices will select the data rate that is most appropriate for the link quality. And that's what it can support. Channel being used by the access point, channel 1, so the range of frequencies supported by this access point. So the access point is on channel 1. And if my laptop wants to communicate or associate with it, my laptop would need to use channel 1. There are some basic data rates that must be supported by the standards, and there are some optional ones. And the optional ones are listed here, the extended supported rates. Some information about the country code, because different countries have different channels available and different rules as how you can use those channels. Most devices are initially configured to work in a particular country or region. But nowadays, they can be managed to change those countries. That is, you can control via software what the device, what country it belongs to. And that's the main information that we see that's of use to us at this stage. And if we look through the probe response that we see captured, we'd see similar information. It's a different frame type, subtype, but most of the other information would be present. Let's say this laptop 10, we know it received a probe response. Actually, we can focus on my laptop. I received some beacons. A beacon from 4C that we just saw, which was saying things that supports 54 megabits per second. Channel 1, WSIT. And I also received beacons from other access points. We saw one other access point. And maybe that supports different characteristics. Does it have to transmit on the same channel? Is my laptop restricted to using channel 1 in this case? What do you think? My laptop or your mobile phone? Is it restricted to using just one channel? Or maybe simpler, do you set the channel on your tablet or mobile phone? No? Has anyone set it? Normally you don't. It's automatically set. On an access point, often you'll set the channel. So when someone configures the access point, they'll say, let's leave this one on channel 6, or in this case on channel 1. Maybe this one was configured for channel 6. But my client device will normally select a channel. And what it does, when it wants to join a network, it's in this scanning, or it goes in a scanning mode. It scans across all possible channels and sees if there are any access points available on any of those channels. So potentially I listen for a short time on channel 1, I received a beacon on channel 1, and then I'll switch to a different channel, channel 2, see if I receive any beacons, and then channel 3, and maybe sometime later I receive a beacon on channel 6. Maybe I'll do this switching between channels for half a second, 1 second, and then after trying all the channels, I will look at all the beacons I've received. In this case, I've received 2 beacons from 2 different access points on channel 1 and 6. Then I would choose the access point to associate with. If I choose this access point, I will switch to channel 1 and initiate the association. So your client often scans through different channels to see what's available. Everyone's okay for another quiz today? We had a quiz last week. We'll have some quizzes as we go. Any questions on the management aspect of wireless LANs? How do we join? How do we discover and how do we join the network? Clear? Anything difficult? You don't know if it's difficult.
How to handle word word.
How do we handle?
Handle word word. How to handle word word when we change to so assume I use the mobile phone and walk out of the range of one access point. So it has to connect to another access point and use the same SSID.
Okay. So this. When you're mobile, of course, you may want to switch between access points. That is, I associate with this access point, and then on channel 1, I'm moving, I'm walking, whatever, and I'm moving in this direction, and my signal to this access point is getting weak. I'm moving away from it. At some point, I'm going to need to use a new access point. If the signal gets too weak and I can no longer receive from it, then I would hope that my device will try and search for a new access point. So it simply initiates the discovery phase again. That is, now if I can no longer receive anything from my existing access point, 4C, then try to discover new access points. Scan through the different channels. Maybe I'll receive a beacon from here and from some other access point, associate. Now, some issues there are if you as the user have told your device to use WSIT, then it will try to automatically associate with the access points that support WSIT. That is, if this is part of the WSIT extended service set, then usually your client software will try to find an access point of the same extended service set. If not, it may automatically connect to another one, or it may prompt something to the user saying, there's another extended service set available, do you want to connect to it?
In this case, do we have to do the re-authentication?
So there's 2 parts there. Do we need to re-authenticate? Within the same extended service set, there's if we see in our slides later, there's a process for doing a fast re-association or authentication. That is, we can omit the authentication if the access points have made some agreement with each other to allow anyone to connect. So we can omit one stage there. If I want to connect to an access point which is a different extended service set, then of course I will need to authenticate fully and associate with that. But connecting to another access point within the same extended service set, there's a shortened procedure for reassociating. Cuts down on some time. That process is called a handover. We hand over from one access point to another. Let's move on. What else have we got? So that's about managing the network. This is just the types of frames available. When we've associated with a network, we can then transfer data, and that's our objective, to transfer data. Let's look at how the data transfer works. The MAC data transfer mechanisms, the aim is to make sure our data transfer is efficient. We have a limited resource available to transfer our data. We need to make use of that efficiently. Robust. We have, in a wireless link, there's often errors and changes in the environment. We want to be able to handle that. And fair. We're operating in an unlicensed spectrum. There may be multiple people wanting to use the same bandwidth as us. So we need to be fair amongst those multiple users. Give everyone equal access to transmit. One thing that we should always remember, since we're using broadcast radio, we'll assume if two nodes transmit at the same time, then there's a collision. Two nodes transmit frames, those frames collide at the receiver, and that results in lost data, and that's bad for performance. So the aim of our MAC is that only one node transmits at a time. If only one sends at a time, there are no collisions and the performance should be better. There are two ways to send in the original 802.11, one called DCF, one called PCF. Distributed coordination function, DCF, and point coordination function. DCF is mandatory, every device must support it. PCF was optional, and it wasn't supported in most of the devices because it was complex and the requirements to use it meant that not many people wanted it. We're going to talk just about DCF. PCF, just briefly, is a polling-based transfer. Access point says, you can transmit, you can transmit, you can transmit. So the access point tells the stations when it's allowed to transmit. In fact, before that, the stations request opportunities to transmit. So the access point controls who sends in PCF. DCF is distributed amongst all the stations as to who transmits. We're going to focus just on DCF. There have been extensions of both of them as well, but we'll cover the basics of DCF only. In DCF, distributed coordination means that all of the stations are participating in working out who gets to transmit. The algorithm's distributed amongst all of them to coordinate who will transmit, with the aim that only one node transmits at a time to avoid collisions. If two transmit at a time, there's a potential for a collision, and that's bad for performance because if the frames collide, no data is received by the receiver and therefore retransmissions will be needed, and if it collides again, more retransmissions and poorer performance. Distributed in that each node implements this function. The set of steps that we're about to go through is implemented in each node. And they determine who can transmit in a distributed manner. Now, in DCF, we treat the clients and access points as the same. We'll call them stations. We have clients in our normal network and they associate with a station, with an access point, sorry. But with respect to transmitting data, they follow the same rules. An access point is no more important than a client in terms of data transfer. So we'll just call them stations, and sometimes we'll ignore whether it's an access point or client. The same rules apply. There are two modes of operation within DCF. One is called basic access, and one is called RTS-CTS. We'll go through basic access and then explain RTS-CTS after that. Which mode do we use? It depends upon how much data we want to send. But again, we'll just go through basic access first and then come back to that point. Now we have data frames, frame type 2. We've seen some management frames, the beacons and probe requests and probe responses. We'll have data frames which contain data. They'll have a header with some fields, the data that we want to send, and some trailer for checksums, error detection. We use acknowledgements. We send a data frame, we receive an acknowledgement. So the basic procedure, a data frame is sent from one station to the other. That receiving station responds with an ACK. The ACKs contain no data. There's no piggybacking happening here. It's just a header. Typical sizes of around 14 bytes, but it may vary in some cases. We'll see in the second mode of operation we have two other frames called RTS and CTS. We'll come back to them. Those three frames, ACK, RTS, CTS, are control frames. They contain no data. They are for controlling the data transfer. The data frame, this is the structure of the data frame in some more detail. The green blocks are the header and the trailer, and here's the frame body, the data. The data may go from 0 up to 2,312 bytes in length. There are some practical limits on that as well. This is the header. We have different fields, and we've seen some of those fields in the beacon frame. There's the same structure. We have frame control field, which is actually multiple fields inside there, 2 bytes in length. A duration field, which we'll see when we talk about RTS-CTS. We have 3 addresses, or 3 address fields here that are used. In fact, there's a 4th address, which is not so commonly used. So 4 address fields, each 6 bytes in length, that is each 48 bits. One address is the source. If my laptop sends a frame, then my laptop's MAC address is the source address. One is the destination. The destination not at the end of the wireless link, but at the end of the other side of the access point. And one is the access point address. So inside here, we'll see later, is an access point. If that's configured and there's a wired LAN cable from the access point to this PC. So I connect wirelessly from my laptop to the access point. The access point has an Ethernet connection to the PC. If I want to send something to the PC, my laptop is the source address. The PC is the destination address. And the access point MAC is the BSS ID, the access point address. So in fact, we have 3 addresses here. The immediate source, or the source, the destination, and the access point. Address 4 is used for bridging. What's bridging, or wireless bridging? What do you think wireless bridging is? Wireless bridging is when we connect two wireless access points together. I take one access point at the top of this building and another access point at the other building and use them in a special mode, bridging mode, and they connect together. So my laptop connects to this access point, or a PC connects to this access point, and then we have a wireless link between the two access points. And then another PC connected to the receiving one. So in that case, we have four entities. The client connected to the first access point, the second access point, and the client connected to the second access point in a wireless bridging link. And that's why we have a fourth address used there. But not so common. Oh well, not a case that we would cover. It's something you would use if you want to connect your home to your friend's home via a cheap wireless LAN link. If you're within range and have line of sight, then you could do that. So we have addresses, we have the data, we have some sequence numbers, so we increment the sequence number. If we have fragmentation, we have fragment numbers as well. We have some error detection capabilities. The trailer contains a sequence of bits for a 32-bit CRC, error detection code, which means that when we receive a frame, we look at the error detection code and look at the data and remember the basic principles of error detection. We apply some function on the data, and if the error detection code matches, then we assume there are no errors. If it doesn't match, we assume that there's some errors somewhere. That's how we know if the frame is successfully received or not. What else? Sequence. And the frame control is on the next slide, I hope. The frame control field is 2 bytes, 16 bits. It has multiple purposes. We saw some of them in the beacon. Indicates the version of the protocol, the type of frame. So this is common across all of them. The subtype indicates the direction of the frame. DS means distribution system. It's the wired portion of the network. So 2DS means it's going to the access point and out to the wired network. From DS is coming from the wired network and coming from the access point to the client. And there's some special cases in a bridging between two access points or between two laptops. Ad hoc mode, no access points. Yep.
What's the difference between bridging and repeating?
Bridging and repeated. In terms of the wireless LAN station, a repeater often is something that increases the signal strength. So it may not be involved in the wireless LAN protocol exchanges. What could I do? I could have my laptop that sends a signal and a repeater receives that and simply repeats, takes a copy of the frame that I've received and sends it exactly as it is. And it sends it, of course, therefore, across a larger distance. I send to the repeater sends across the next link. In that case, we'd think the repeater simply repeats the signal that I received. It doesn't do any processing of the frame, receives the frame and sends it on. So the receiver from the repeater thinks it came directly from my laptop. It knows no difference. So the repeater just repeats the signal. A bridge does some processing on the frame. If this access point is acting as a bridge, I transmit a frame to it, it receives and does some processing and potentially modifies that frame according to the protocol and sends it onto the next device. For example, it changes the addresses. I send it to the access point, it will change to send to another access point in bridging mode, it will change the address which it came from. It came from this device. So with a bridge, the eventual destination knows that it came from a bridging device, In a repeater, the eventual destination thinks it came from the original source device. It simply repeats the signal. That's the best distinction I think you can make of the two. When you buy a product, maybe different marketing will use different terms, but I think that's the more technical distinction. Here we don't worry about repeaters. We're talking just about access points and in bridging mode where they are not repeaters but bridges. If we perform fragmentation, we set some field, some flag to 1. If we have to retransmit a data frame, we set some flag to 1 to indicate it's a retransmission. It's not the original. And some other features. Do we use power save mode? Do we use encryption? And something used if we use multicast. So these are all single bit flags and some 2 and 4 bit fields inside the frame control first 2 bytes. With the addressing, we saw that there were 4 addresses actually. The 4th one is used for bridging. The other 3 are always used. They're all 48-bit MAC or hardware addresses. So that structure of 48 bits, or we don't have it in hexadecimal, 12 digits. The 3 of them that are most commonly used are the ones that identify the client, the access point, and the LAN address. Yeah?
If in ad hoc mode, then there will be no AP, right?
Yes. So
Then what is the third address?
then we'd ignore that. That is, in the header, we have 4 addresses. In some modes, we don't use them all. It doesn't matter what the value is, we'd ignore them. In bridging mode, we use all 4, so we'd look at the 4th address. Connecting to an access point without bridging, we just use 3, so we'd ignore address 4. Connecting in ad hoc mode, laptop to laptop, no access point, we just use 2 addresses, so we'd ignore the other 2. Okay? So there's all values there, but we only take into account the ones that are needed. Has anyone set up ad hoc network or ad hoc link between 2 laptops or between 2 devices? If I ask you in the assignment to complete it by next week to set up an ad hoc link, can you do that? When you demonstrate you can do it? Have you done it before? Most mobile phones will be able to do it. Connect direct between the 2 devices. That's what the ad hoc terminology is used for. A direct client-to-client link. Although we're not talking about that, we use examples with access points. The data transfer phase is the same. Three addresses. Examples of how they're used. We're sending from our client on the wireless LAN to some PC on the wired LAN, as an example. These are our laptops. It's an old picture from many years ago where most of the wireless cards in laptops were not built in, but you had to buy an extra card and insert it in. Nowadays they're all built in. Here's our client, access point, and PC. They all have MAC addresses. If I'm sending to the PC, then this is address 1 in the frame header, address 2 and address 3. That is, address 1 is the immediate destination, the access point. Address 2 is the immediate source, the one who's sending the frame. Destination, source. Address 3 is the eventual destination. Going the other way, sending from our PC back to the client, we send the frame We send an Ethernet frame across the wired network. It arrives at the access point. When the access point sends that frame to my laptop, there are 3 addresses. The immediate source, address 1, the immediate destination, my client, the immediate source, the access point, and the original source, the PC. So 3 addresses included in the wireless LAN frames. All MAC addresses. One final case, laptop to laptop, mobile or client to client on the wireless LAN. Immediate destination, immediate source, final destination, the client here. With the fact that it's another wireless LAN device compared to an Ethernet device makes no difference there. Now let's look at data transfer. Before we do so, let's see if we can find an example of a frame in our capture. Before I filtered for frames of type 0, that is management frames, now let's look for a data frame. We have a set of data frames captured. Wonder if we can see something that makes some sense. Here's something some of you will recognise. It's a data frame captured on the wireless LAN, captured by my laptop. And it turns out this one's a TCP SYNAC segment, part of the TCP connection setup between, in this case, a web browser and a web server. So this was sent by the web server. We have the 802.11 header fields, the frame header, and inside this frame is an IP packet and a TCP segment. If we draw it, it contains no data. Remember, the wireless LAN frame, or the wireless LAN frame structure, has a header and a trailer. The frame check sequence here, the error detection. Just shows some of those values that we've looked through on the structure of the frame. The type of frame, it's a data frame, it's a normal data frame, the subtype. Destination address, the MAC address of the destination. Access point address, BSS ID, and the source address. And inside the wireless LAN frame, it's an IP datagram. We can see the source address and the destination address. The destination address, I guess, is some laptop or probably some laptop or mobile phone inside SIT. A 10.10.99.172 address indicates it's a local address. And the source address, because of the port numbers, indicates it's coming from a web server. So someone on their phone or laptop has access to web server or tried to connect to a web server. They send a SYN segment to the web server to establish the connection. This is the SYN MAC coming back in the establishment of the connection. Coming back from the server because the source port is 80. Destination is probably that of a browser. This is the web server address. This is the client address. Note that which direction is it going? Does it tell us? These 2 bits, or this 2-bit header field in the frame control tells us the direction of this frame. It's going from DS. DS is the distribution system. Think of it as the wired portion of the network. We have our wireless LAN connected to the rest of the network. That's what the DS is, the distribution system. From the wired network to a station, to a client, via the access point. So it's coming from the wired network to the access point. The access point is transmitting this frame to the client. Let's say here's our client, laptop. Maybe it was, well, some access point nearby, we don't know which one. And this access point has a wired network, an Ethernet switch, and somewhere out on the internet, some server, some running web server, and the address is the address of the web server, 118.215.125.15. That's our web server. It's a web server. It's using port 80. Here's our laptop or our client device, maybe a phone, with address 10.10.99.172. Running some web browser, most likely, if it's connecting to a web server, using port 49484. And this frame that we've captured here was captured by my laptop. It was in a mode to take copies of all frames sent from the, it was sent from the access point to the client. And because my laptop was in range, it received a copy as well. We can think it was transmitted all around the access point. My laptop received a copy and is showing us here. The access point address is this one, 50B0. Sounds like it's this access point, the one we saw before, not a different one. The source address is the address of the device on the wired portion of the network. But be careful, it's not necessarily this device. It's the address of the device on the LAN that the access point is attached to. If this is a router, most likely the address 00B2 is that of the router. The access point here is 50B0, and the destination is the client device, which is 68 through to 11. So that's where we see those three addresses come into play. Access point address, client or wireless device address, and address of the device on the LAN that they're communicating. We don't know if this address is for this device or a router. We cannot tell from this information. Any questions before we move on to the data transfer part? How does the data transfer work? When's the first part of your assignment due? Do you remember? Did I tell you? When's it due? It's due next week. So let's talk a little bit about the assignment. Who doesn't have a group? 1, 2, your group now. Okay, that's the final group. So we have nine groups, I think. Yep, 7 groups of 3 and 2 groups of 2. Okay, so everyone's now registered their groups. We have 9 groups. Your group number 9. Okay, everyone else has a group number. Who is group number 8? Okay, someone. So you have a group number G01 or G02. You'll use that in setting up your access point. The assignment's worth 25% of the course score, so it counts a significant part. The other main parts are the exams. The final deadline is to be announced and some of the rules, because it's going to go in phases, 3 phases at least. The assignment's about understanding the performance of wireless LANs and transport protocols. So not just wireless LANs, also transport protocols in wired networks. TCP is the main one. So the first phase is that you need to set up your own wireless LAN. So we have 9 access points. I only have 2 here. The rest you can collect, or someone can collect these. So we have 9 access points, and each group will have one, and you need to configure the device in the first phase. Very simple task. And then in subsequent phases of the assignment, which will run past the midterm, so the first phase will be due next week, and then the second phase just before the midterm, and the final phase after the midterm sometime. In the first phase, you will set up the wireless LAN, just learn about the device, so just a discovery phase. And the second phase, you'll do some experiments to measure the performance of data transfer in the wireless LAN, and compare it against a wired LAN using the device. And in phase 3, you'll do some more in-depth performance analysis, looking at how TCP impacts upon performance. Of course, you can only really do that after we have the lecture on TCP, which is before and slightly after the midterm. Let's go and concentrate on the first phase. It's a group assignment, so you should do this in your group, and in some cases, especially in phase 2 and 3, I may ask you to do individual tasks per member. The groups of 3 will be required to do more than the groups of 2. The groups of 2 sometimes. But the first phase is easy. You collect your access point. There are 2 here, there are other 7 with the technician, the IT technician in the Macintosh lab. So that's where you'll collect them from. You can use them throughout the assignment. They have some firmware on them already. They are Linksys access points, reasonably, well, getting old now, but quite reliable. We're going to use some different firmware to run on these, to allow us to do a few different things than what's normal. So the access point's a computer, really. It's a computer, but you don't have much control over it. unless you change the firmware, the software running on it. So there are different free firmware packages that can be installed on some access points. The one you're going to install is called OpenWRT. It allows you to do, it's a cut down Linux version of Linux that is installed on the device and allows you to install different software on there and do more things that you can do with the default firmware. So really your task in phase 1 is to install that and configure the access point. Here I mention the version of the software, the firmware to use. There are different versions. The version you need to use is called Backfire 10.03.1 and kernel 2.4. You'll see that when you go to the OpenWRT website, and I have a link to the firmware image there. Now, you need to be careful and follow the instructions. If you do something wrong when you install the firmware, the device won't work and you'll fail that phase. Okay? If you break the device, there will be consequences. Usually in terms of marks, maybe financial consequences if you have to buy a new one. Okay? But the only way that you can mess up the installation of the full firmware is if you don't follow the instructions. The instructions are quite straightforward. In this case, it's quite hard to go wrong unless you try something different and try to do a shortcut. So on the website for OpenWRT, it lists the set of supported devices. From there you'll find this device, and on that web page there's the instructions for how to install the firmware. This is the page. The page has other information as well, so read through it. Some of it's relevant, some of it's not. Some of it's about the hardware aspects, but eventually when you read through this page, you'll find something that says, these are the steps you must do to install the firmware. Read them carefully before you do it, because that is, read it all through before you start. Once you install the firmware, then there's a command line access to the device as well as a web page access. That is, you can open up your web browser, browse to its IP address and configure it by clicking on some buttons and so on and setting it up. And you can also log into the router using Secure Shell and configure it via the command line and do different things like install software on it. We may use some software on it to do the experiments in phase 2 and 3. Let's look at the device. Let's look at the device here and then a picture of the device, the access point. So it's a wireless LAN router. But it's in fact multiple network devices in one. It's a switch. You'll see that there are 5 Ethernet LAN ports on the back. One is labelled Internet, the other 4, 1, 2, 3, 4. So the basic mode is that the Internet port you connect to your wired LAN, which connects to the Internet, provides the net access. And then the other 4 ports are for connecting PCs on the local LAN to the device. So you can use it simply as a switch and as a router. So it's a router and a switch. The router connects the Internet port to all the other devices attached to it. And it's a switch in that you can connect 4 PCs to it and communicate between them on the same LAN. And it's a wireless LAN access point at the same time. We have the wireless chip inside. And because it's got a CPU, it's a computer in there, it can do software-based things. It can act as a firewall and many other things. On this website, there's a picture of the internals, or a block diagram of the internals. That's it there. What we see So this is our device, but looking at the interfaces to it. There are 4 LAN ports on the switch, 1, 2, 3, 4, and the internet port. So there are 5 places to plug the cables into. Really, internally, from the device's perspective, that's just one big switch with those 5 ports plus another port. There's nothing you can plug a cable into, but internal on the board, there's a connection from there to the CPU. Okay. So here's our CPU, and from its perspective, it has 2 LAN interfaces. And the LAN interfaces are labelled ETH0 and ETH1. One LAN interface to the switch and one to the access point. So that's why you can think of it as multiple devices connected together. Or if you go and buy an access point, this is more than just an access point, but if you go and buy a device which is just an access point, and that's it here, then you go and buy a switch, a 6-port switch, and then you have your PC, your computer, somewhere. And the PC has 2 LAN ports. Then it's as if you connect your PC to the switch and your PC to the access point. So it's as if you have those 3 devices inside here. These connections are just internal on the hardware. So your PC or your CPU has 2 LAN interfaces, ETH0 and ETH, well, it's just ETH, I thought it was ETH1. And the switch allows you to connect other devices to it, 5 other devices. So that's the internal structure, and because it's the CPU, we can run software on it, and we can do things like run a firewall, run a web server, run a BitTorrent client, run any software in theory, so long as it's small enough footprint to install on the limited memory that it has inside. Back to our assignment. So, your task this week, and before, I don't know if I said it in the email, but the intention was before the lecture next week, install OpenWRT on the device. There are not many options, you just follow the instructions, but then you can configure the device. And 2 things you must do: set the host name to your group ID. So there'll be one device will be G01, one will be G02, G03, and there'll be G09. So the host name, and you set the password to the device. There's only one user by default, the root user, and set the password on everyone's device to ITS413. That's okay for now. The wireless LAN may not be enabled by default. So you need to enable it, test that it works, set the extended service set ID to your group ID, G01, G04, G09. And then try it. Try it by connecting a laptop via the wireless link and connecting a laptop or a PC via the wired link, and see if they can communicate with each other. So connect a laptop here wirelessly and connect another computer here, and they should be able to communicate with each other. So you should be able to test that basic communications. And you could test 2 laptops communicating to each other wirelessly and other variations. And be prepared to learn how it works, because in the subsequent phases you will need to use the interface, both the command line and the web interface, to run some tests using it, to change different parameters so that you can investigate the performance. Any questions on the assignment? Due next week. if you don't have access to a laptop, then we have some computers with wireless cards that you can use. And in fact, even if you have access to a laptop, you can use them. In the third floor, you know, where the Macintosh lab is in the other building, on the same floor there's the research lab there. Inside that room, in one of the corner rooms, you'll have to find it, there's no room number on it, there's some 3 PCs in there, or at least 3 PCs, and 2 of them have wireless LAN. In fact, there's 3 PCs with wireless LAN cards in there, configured with Windows and Linux on them, so you can use them for the wireless testing if you want. In fact, if you don't want to carry around your access points with you all the time, you can leave them in that room. Does anyone know the room I'm talking about? Do you know where? Is there a card reader there? No, there's a fingerprint reader there, but it doesn't work. Do you know where we used the faculty members from ICT used to sit? In the other building? Were you here when we were not in this building? Anyone remember? We moved to this building 2 or 3 years ago. Maybe you arrived, we were here. So 3rd floor, not in the Macintosh room, but in the research lab there. And as you walk in the door, it's the far room across the diagonal. Ask someone there, you'll find it. Ask for my room. Just there's no... One room is a sound room, it's not that. 2 rooms, one's a music room, one's a sound room, one has a robot in it, and one has controls for cameras. And the other one's locked. It's the one that's not those, okay? So you'll find it. One last thing. In the subsequent phases, we'll use some software called iPerf to do some tests and some other software. Some of the tests will require Linux. So at least one of your computers would need to run a Linux operating system. Now, if you cannot get that on your own computer, again, those computers in that room support it. You can use them. So you will need that in subsequent phases. Let's start on how we transfer data over a wireless LAN. It's a random access, medium access control protocol. Remember how random access works? In our lecture last semester, we said we had things like centralized and distributed MAC protocols, a round robin MAC protocol where was when everyone takes in turn, one node transmits, then the other one, and then we come back. That was round robin. That requires either some token to pass between them or some centralized control. We had a reservation-based scheme where the stations would reserve their chances to transmit, and a random access scheme. Everyone just transmits when they want, under some conditions. The conditions being that transmit so long as no one else is transmitting. If you detect someone else transmitting, then wait for some random period and try again. And that's what we'll see that how wireless LAN works. Random access MAC protocol called DCF. Remember, clients and access points are the same from this procedure's perspective. They are stations. The basic concept is a station will transmit if the medium is idle. The medium is the wireless transmission medium that we're using. Medium being idle means that no one else is transmitting. How do I know no one's transmitting? Well, I turn on my receiver. If I receive nothing for some period of time, then I'll assume no one's transmitting. If I receive something, then I assume someone else is transmitting. So we can detect if someone's transmitting by listening using our receiver. A station will transmit if the medium is idle. If it's busy, if I turn on my receiver and I hear someone else transmitting, the medium is busy, then wait until they're finished, until it's not busy, and then transmit. But there are some more details there. Not transmit immediately, there are some extra rules. Remember, the goal is that only one station transmits at a time. Imagine all of you are stations, everyone wants to say something, you need to coordinate amongst yourselves that only one of you talks at a time. So that's the goal. When a station has data to send, let's say I have some data to send from an application, a frame, one data frame, what I do is I wait for the medium, or I check the medium. The medium must be idle for some period of time. Idle means no one else is sending. That period of time is defined. It's called the DCF interframe space. You'll see IFS is the interframe space. So this is diffs, the DCF interframe space. So I have my receiver going. Let's say diffs is 50 microseconds. Then for that 50 microseconds, I listen on the receiver. If there's no signal being received, then I assume it's been idle for that period, and I move to the next step. So if the medium is idle for that duration of diffs, then check again. The medium must be idle for some further period, called the back-off period. And this back-off period is not fixed, it's based on a random number. Diffs is fixed, some fixed value. Every station has the same value. The back-off period we'll see later changes. If, say, the back-off period is 100 microseconds, I listen for 100 microseconds. I don't receive anything. The medium was idle. I move to step 3. That is, the back-off is complete. Then I send my data frame. Transmit my data frame. Takes some period of time. I transmit my data frame. A station receives it. If they receive that data frame successfully, they'll wait a short period of time and transmit an ACK back. When I receive the ACK, I've finished that data transfer of the one frame. That's the normal case. In summary, wait, or the medium needs to be idle for the DCF interframe space, the diffs, and then for a back-off period, and then I transmit, then I receive an ACK. What if the medium becomes busy? What if it doesn't work like that? That is, I want to send some data. I check if anyone's transmitting. During the diffs period, I find that someone starts transmitting. The medium becomes busy. Then I wait until it becomes idle and then restart that procedure. Go back to the start. So I've got data to send. I check, is anyone else sending? Yes, they are. Okay, I wait, I listen, they're still sending, they're sending, they're sending. The medium's still busy. When they stop sending, the medium becomes idle, I go back and start again and try the steps again. If we complete the diffs period, the medium is idle, and we enter stage 2 where we're waiting for the back-off period, the medium must be idle again. If someone is transmitting during that period, then we'll must wait for the medium to become idle again, and then we'll come back and continue from where we left off in this back-off period. We'll have to come back to explain that back-off in a moment. Let's demonstrate that with a simple example. These examples show, and you'll see these and you'll have to draw these in exams and so on. What it shows is 3 stations, A, B and C, and it shows the steps that they perform over time. So time increases as we go to the right. And it's illustrating what's happening with from the perspective of each station. In this example, station A wants to send some data to B at this point in time here. So when it has data to send, a single frame, it checks if anyone else is sending. And it does so for a fixed period of time called diffs. And that's what's shown here. For this period of time, A is checking, anyone else sending? No, no one else is sending for this period of time. Once that's completed, it does it again, but for a different period of time called the back-off period, shown here. Check, is anyone else sending? No, 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 no one's sending, no one's sending, the mediums are idle. If we complete this period, then we transmit the data. And this rectangle is showing the transmission of the data. This greyed out box under the data is showing that someone is transmitting. Looking at the other stations, B and C, which happen at the same time. At this point in time, no one's transmitting. B has nothing to send, it's doing nothing. C is doing nothing. We'll come back to C in a moment. From B's perspective, it's doing nothing. And then at this point in time, the medium becomes busy. The medium is busy now because A is transmitting. So these grey boxes indicate whether the medium is busy or not. If there's a grey box there, from that station's perspective, it's busy. It's busy. In fact, A is transmitting, B is receiving. When that entire data frame has been transmitted, B has received it. Remember, A was sending to B. A is the source, B is the destination. When that entire data frame is received, B waits for a short period of time. And this is fixed. It's called the short interframe space. Diffs is the DCF interframe space. SIFs is the short interframe space. It's shorter than diffs. Wait for a short time and then send back the ACK. So B starts transmitting the ACK, and from A's perspective, the medium is busy. In fact, A is receiving the ACK. And when the ACK has been transmitted in its entirety, and A has received that, then that data transfer is complete. Started here, diffs, back off, transmit the data frame, short interframe space, transmit the ACK. At this point in time, that one data frame has been transferred from A to B. That's the basic procedure. If everything goes well, that is, if no one else is transmitting. If we look at B and A still, A sent data to B, let's say just as an example, then B wants to send some data back to A. So it does the same steps. Check if no one else is transmitting for diffs, back off for some period of time. If no one's sending, transmit the data. A receives the data. When A has received the data in its entirety, it waits for a short interframe space and sends back the ACK. So from here, data to A, to here, the ACK is received. The second data frame has been sent from B to A. There are two examples of a success.
Is there a possibility that during SIFs the medium becomes busy?
So the question is there a chance that during a short interframe space the medium becomes busy? There's a small chance, but it's unlikely. The reason it's unlikely is that, and we'll see later when we look at the back off and the durations, it is a very short period such that no one else should be able to get the opportunity to transmit because they need to wait a longer period for the medium to become idle. There are some chances that will happen if we have something that we mentioned before, this hidden terminal problem, but that's a special case. It's unlikely that it will happen for now. We'll see a case later. So, data transfer. Wait for diffs. Wait for the back off. The medium must be idle for those 2 periods of time. If so, transmit your data frame, then receive the ACK. Last example before we finish for the day. Station C, at this point in time, has some data to send to B. A had some data to send to B. C is another laptop in the network, also wants to send something to B. It doesn't know what A is doing, doesn't care. So it follows the same rules. The medium must be idle for that entire duration of diffs. It's checking, is the medium idle? Yes. No one's sending, no one's sending. It's idle, it's idle. Medium becomes busy. It's busy because A is now transmitting. So long as A, B and C are within range of each other, if A is transmitting to B, C will also hear that transmission. And C will know that the medium is busy now. So it interrupts the process from C's perspective. We say that C defers until the medium becomes idle again. So we say the medium is busy, so it's deferring, waiting for it to become idle, waiting. It becomes idle again because A has stopped transmitting, B is waiting for the short interframe space. So now C starts the procedure again. We need the medium to be idle for diffs. It's idle, it's idle, it's idle. We're interrupted again because B is transmitting the ACK now. That means the medium is busy. Therefore, we defer until it becomes idle again and start again. Wait for the diffs, back off and try again. Now we see there, related to the question, because the short interframe space is shorter than the DCF interframe space, diffs, by definition it's shorter, both of these stations, B and C, had the medium to be busy at the same time and it became idle at the same time. B had to wait for the short interframe space before it could send the ACK. C had to wait for the DCF interframe space, which is longer, before it could start the back off. If they both start at the same time, B will always finish first, or the station that has to wait for the short interframe space will always finish first and transmit the ACK before someone completes the diffs, because CIFS is shorter than diffs. And that's why it's unlikely that someone will transmit and the medium become busy in that short interframe space. Basic procedure, diffs, back off, transmit data, CIFS, ACK. If you're interrupted during the diffs or back off by someone else sending, you defer, you wait, and then try again. That is, restart if you're interrupted during the diffs until you have some idle period for long enough. Try the back off. If your back off is interrupted, you must also defer and try again. There are some more details about the back off and the size and how we try again, but that's the basic procedure. And it's all we have time to cover today.